are going to set up a little virtual network with VPP, so that will give us the occasion to see how we create virtual interfaces such as tap interfaces, virtual Ethernet interfaces, VETs, which are both Linux ways to make virtual interfaces. And we are going to make a little bridged first, and then routed network using those interfaces, but within VPP, I mean. So you can open this page here. It's on the wiki. This page was secretly created especially for this training. It's available. It has been available for a few days, but for now there is no link pointing to it. So you have to type the URL. So tutorial routing and switching. So this is a tutorial with all the commands we are going to type to set up the network. But before we start, let me just show you what we are going to do and explain a little bit what tap and virtual Ethernet interfaces are. I mean, if it's necessary. So raise your hand if you know what a tap interface is. Yeah. Okay. Virtual Ethernet interfaces. Okay, almost everybody. Very quickly, so the tap interface is a way for, I'm going to use this. It's a way for a process to have on its side, on the process side, a way to send and receive packets that are going to the two Linux system. So on one side you have an interface that looks like a physical interface, but instead of being the packet, instead of being sent or received on the interface, they are sent to a process. So that means that in VPP, when you create a tap interface, you will have that tap interface living in Linux. So Linux is going to, when for instance someone on the system sends a packet, like open a socket, sends a packet, and the packet happens to be routed to that interface, that tap interface, the Ethernet packet is going to go to VPP. So the packet goes this way from Linux to the tap interface, goes out, I mean virtually out to Linux and to VPP, and then VPP receives the packet. Virtual Ethernet interfaces are different, and they are not used the same way in VPP. When you create virtual Ethernet interfaces pair, because they always go by pair, everything that Linux sends on one side goes out on the other side and vice versa. And so what we do with VPP is just that we tell VPP to open a socket and use AF packet. So it's an AF packet interface using an optimization that is available in Linux with AF packet is instead of sending and receiving the packet using system calls, it uses shared memory. So right now, AF packet interfaces are more efficient in VPP than tap interfaces because they use shared memory. They don't use system calls for every packet. So in our setup, a point about namespaces. I think everybody knows what a namespace is and what a network namespace is. In this setup, we are going to use 4 different namespaces. There will be the main one, the default namespace, where VPP is going to run. There will be then NS0, NS1, and NS2. And so when we want to have a tap interface within a namespace, then we just tell VPP to create the tap interface. It's going to spawn it. It's going to exist. And then using standard commands like IP, we can move the tap interface from the default namespace where it's being created to NS2. So in that situation, we are going to have VPP in one namespace and the tap interface is actually living in another namespace. That's not a problem. That's okay to receive and send packets. That would be a problem if the interface here between the tap and VPP was a socket. If that interface was a socket, then you could not do that because you would have VPP and the tap in different namespaces. That wouldn't work. But it's not a socket. This interface here is a file. So you can live in different network namespaces but still access a tap. Here it's different. When you use AF packet, when VPP plugs to VNet using AF packet, here it's a socket that it uses. So you have on one side a virtual Ethernet interface that is living on the default namespace. And VPP is connected to that interface using AF packet. And virtual Ethernet go by pair. So we have the other virtual Ethernet in the other namespace. So everything that VPP sends using a socket on one side goes to Linux and goes out on the other side to Linux still, where we can send and receive packets. So you have two ways of doing this lab. You can either use VPPCTL all the way and do sudo VPPCTL and every command, or you can. So I don't know if my VPP is running right now. So you can either do that for every command that we are going to type, or we can stop VPP and we can do make run from or make run release, depending, from the VPP directory. Okay, I need to do run release because I didn't build the debug one, but for this this lab, it's not going to make any difference. You can run either the release. So here is the console. I'm going to put it up, and the lab. So it shouldn't be too complicated because everything is written as command. I mean, it's just copy paste. So yeah, here I just used make. Oh, it's not this one. I just used make run, but there is a third way actually that you can start VPP. It's with the binary. You can just give a few arguments. As Damien explained, interactive in Unix is going to ask VPP to run in interactive mode such that you can get the CLI. And the rest is our other features like API address for the API anyway.
You can just have the content of the startup file
as absolutely, they are in. Actually, it's how it's done. When you do start VPP, it's just taking the file and using it as a CLI, as the command arguments. So first, you already saw this show interface. So it's for every command in general. You can just do so you have show interface. You can just do show int, and it's going to work. The CLI is going to autocomplete as much as it can. I don't know. So if you have if you want to know the commands that are available, you can do just question mark. Question mark is going to show you all the commands, all the CLI commands that are available. But the question mark can also be used to autocomplete. I mean, it's exactly the same as in Cisco routers, for those who know, and probably in other devices as well. So anytime you don't remember what is the command, you can just put a question mark, and it's going to autocomplete. Like if we do show question mark, then we see that we can do show affinity, show buffers, etc., etc. There is a bunch of commands just to display information. So let's start with creating the namespaces. So first, we are going to create the namespace 0, and here you just have to go to not VPP, like the. I need to start a different. Okay, so some commands have to be typed in Linux, such as all the Linux commands. So I need to go to my Vagrant file. Okay, so I have VPP on one side and Linux on the other. And let's just create those. So the first one creates the namespace, the second one creates virtual Ethernet. Then we move one side of the virtual Ethernet to the other. So right now,
If I do IP link, I can see VPP0, which is one side. And because I already executed this command, the other side, the other virtual Ethernet is already in the namespace 0. One trick when you create a namespace is to not forget to set the loopback interface up, because initially it's not up. And if you forget to set it up, then you cannot send or receive packets. So here we set the different interfaces up. Then we set an IPv6 prefix, still within the namespace. So for those who are not used to use IPNetNS, you see that all my commands here are prefixed by IPNetNS exec ns0. That is going to execute a command just like if it was executed within the namespace ns0. Okay, so the second namespace, ns1. Same story, we create virtual Ethernet. So right now we just changed Linux configuration. We didn't do anything with VPP. So yeah, I'm going to remove that from the screen, but just go to the wiki page and copy paste all these commands in Linux as super user, as root, and it will work. All right. So on the VPP side now, let's go to the interesting part. We are going to create the AF packet interfaces that are going to be connected to the virtual Ethernet. Virtual Ethernet being, so we are going to tell VPP here, host interface, to connect to virtual Ethernet NS1, virtual Ethernet NS2, NS0, which are on the default namespace here, on the same as VPP namespace. So actually, if we just do a IP link, we can see those two interfaces, VPP0 and VPP1. They are here. They are in the default namespace. So when we do VPPCTL, create host interface, name VPP0. No VPPCTL for me, because I'm already there. Up, create, and now if I do show int, I have host-VPP0 there. Anytime you create an host interface, also known as AF packet interface, the name of that interface is going to be host- and the name of the interface on Linux side. So here, host-VPP0. I do the same for VPP1. Oh, crap. Here it is. And now host-VPP1 is created. And if I do show int, I get the two interfaces. Host VPP0 and host VPP1 are created in VPP. Yes, sir. So first of all, when you do the question mark, there is the command on the left side, and then you have a help. No, you have on the right side. You have the arguments most of the time. It's not all arguments are documented. It's on his way, and as Damian said, the CLI is not something. It's really for debug. It's not for production. The CLI can change anytime. We do not make it stable. I mean, when we add features, we change the CLI. The API is going to be maintained. The API, we will not change it unless releases and so on. The APIs will be, yeah, there will be consistency, but the CLI, there is no insurance that we don't change anything. But anyway, so for your question, here you get a little help. And then in the wiki, there is a wiki page with more information. It's the wiki page called Command Line Interface CLI Guide. So we try to keep it up to date. There might be things that are different and so on because the CLI is moving very fast, very quick. So here you have documentation about most of the important CLI commands. Like, it goes from show interface, show hardware. I mean, all the things we are going to use for this hands-on, they are explained in that command line, VPP/command line interface CLI on the wiki. One difference between DPDK and interface and AF packet interface is that when you connect a VNet, an AF packet interface to VPP, the interface does not disappear from Linux. With DPDK, when you give an interface to VPP, the interface is gone. It's owned by VPP. But with AF packets, when you ask VPP to use AF packet, and you can do that for any kind of interface, even physical interface, all the interfaces that are on Linux, you can do an AF packet, an host interface. So VPP is just going to open a socket, a raw socket on that interface, and use AF packet, shared memory to make it more efficient. So for instance, if at some point you have an interface that is not supported by DPDK, but it is supported by Linux, you can plug VPP and that interface together by using AF packets, so host interface. It does not need to be a virtual Ethernet interface. Here it's just an example. Okay, so just to rephrase the question was what happens when a packet arrives on an AF packet interface? Because AF packet, the interface stays in Linux, so you can still have processes like Wireshark that listen on that interface, and VPP listen on that interface as well. So VPP will get duplicates of the packet, so it's not exclusive. You can have many processes using AF packet at the same time. It's like raw socket, layer 2 raw socket. It's not, if you open a raw socket this way, doesn't mean that Linux is not going to receive the packets and so on. Except that we use a shared memory interface that is implemented by Linux. So it's more efficient than just using system calls. And if, like in the cases where VPP is actually the only process that is on the interface, it's pretty efficient. It's not as efficient as DPDK, but it's okay. Here we are using our own. It's like we have our own tap interface driver, AF packet driver, vhost user driver in VPP, I mean, non-DPDK. And we used to have a few drivers as well, but they are deprecated now. And maybe vhost user will be deprecated at some point if DPDK is good enough. I mean, we have both right now. We can use either. So we created the two interfaces, the AF packet interfaces. We are now setting them up. So we do set interface state host the name of the interface up. We can also do so with shortcuts if we want, but we cannot do shortcuts with the interface name. See, so this command works as well, but well, here it is. So now, if we do show interface, we see the two interfaces and they are up. And show hardware. We see as well in hardware, although they are not hardware, they are virtual interfaces. We can see so the Ethernet address and the fact that it's a Linux packet socket interface, the type of the interface. So I don't think. Okay, so now before we start configuring the bridge, we are actually going to make the third namespace called NS2. We are going to create from scratch a tap interface, and that can be done in VPP. So for the virtual Ethernet, we did it in Linux first, and then we asked VPP to connect to it. For a tap interface, we create it in VPP. Tap connect tap 0, and no interface tap 0 was created. And we can see it here. It's down for now. But before we set it up, we are going to, so this time on the Linux side, we are going to configure the third namespace that we are going to use. it's exactly the same thing as previously. We create the namespace. We moved, actually, yeah, that I forgot to show, but we moved the interface tab 0 to namespace 2. Like, if I show the interfaces that are now available in NS2, we can see tab 0. We moved it right now from the default namespace to NS0, to NS2. So we moved it. I'm going to set it up and configure the IP addresses. Yes, it's tab connect tab 0, and actually no, there are two ways. I think tab connect is going to be deprecated, right? It's supposed to become create tab, something like that. First, we are going to do switching between the two virtual Ethernet interfaces that we created. So first of all, we want to enable bridging, because by default, all interfaces are in routing mode. So they are connected to the routing engine. If we want to connect an interface to a bridge, we use this command, set interface L2 bridge, the name of the interface here. And then we give the bridge domain ID. So here we are going to create the bridge domain ID 1. And same thing for the second interface. And that's basically all, normally. If I do trace, but you will have more detail about tracing packets in this afternoon session. But so right now, we are in a setup where those two interfaces are actually bridged using this bridge domain, and the ID of this bridge domain is 1. Oops. And I can do ping. So here I'm pinging from, I think, this namespace. Oh, no, sorry, this one. Or there is a mistake in my schema here. But I'm pinging from here. It goes to the bridge, then it goes back, and the other namespace is replying to the ping. So because I did trace add IF packet input 8, VPP has traced 8 packets. I can do show trace, and it's going to show me the packets that went through here. So we can see, like, this is well, we don't see much information because it's only bridging. But so this is the ping echo and request and response that are traced. So we can see the MAC addresses, etc., etc. Again, more to come in this afternoon session about packet tracing. I didn't show the bridge. So yeah, with the command show, so the full command is, I think, show bridge domain. With show bridge domain, you can see that we have the bridge domain 1, which exists. And I think with show bridge domain details or verbose, I can see that the bridge domain 1 has host VPP 0 and host VPP 1 connected. Yeah, so the next step now is to connect the bridge we created to the VPP routing part. Right now, right now we have those two interfaces connected, but we don't have a loopback interface here to connect bridging to routing. So we need to create one. In order to create one, we use create loopback interface. That just spawns a loopback interface that is called loop0. You can see it with showInt. It's right here. We do set interface L2 bridge loop1 1. So that command is exactly the same command as we did with the virtual Ethernet commands to set them, to connect them to the bridge domain 1. We just add the special keyword BVI, which means bridge virtual interface, I think, which means that loop0 is going to be the way VPP can receive packet from the bridge. So with BVI. So now if we do show bridge domain 1 detail, we see the third interface, loop 0, and we see that that bridge domain, the one, has a BVI interface called loop 0. So now, I mean, almost there. Once we set loop 0 up, now VPP is capable of receiving packets coming through the bridge. So yeah, let's configure IP addresses on the loopback interfaces. So this is for IPv6. This is for IPv4. Now VPP is configured with the local, link local IP addresses, the prefixes. Again, we can do trace add that to trace packet coming and going. And we can ping from Linux through the bridge, but this time we are not going to ping the other VET's namespace. We are going to ping VPP directly. And here, in that case, the packet goes from one namespace, it goes through the virtual Ethernet, it goes to host interface, the bridge, and then it goes to the loopback interface, and VPP receives the packet because it's a local packet. It's using his destination address, and so it replies to the ping. So here it's with IPv6. We can do the same with IPv4. So you can see that the first, when you ping, the first delay is actually quite big compared to the others. That's because of a VPP trick, which is that when you try to send a packet with VPP, if the neighbor is unknown, that packet is actually transformed into an ARP request or a neighbor discovery request, and the packet is not stored. The packet is just transformed into a request and sent on the wire. So the first ping is actually lost, and it's the first neighbor discovery request is lost, and it's only the second one that works. So now we can do show trace, and again show the packets. Now that we have more IP addresses, we can do show L2 FIB verbose. So show L2 FIB is going to show you the layer 2 FIB, the sort of routing table with the MAC addresses. And so we can see the different MAC addresses that are known by the bridge. So this MAC address is the MAC address of the virtual Ethernet interface on Linux side. If I do IP link here, so we see that on Linux, that interface is this one. It's right here. And if I do NS1, I see the other MAC address, which is this one. Finally, let's do some routing. We have a few minutes left. In the routing parts, we do set interface state tab 0 up to set the interface tab 0 up. So just to remind everybody, the tap interface is on this side here. Let's configure the IP addresses for this interface on VPP. And so now that we added, actually, yeah, I didn't show the FIB yet, but one very useful command, show IP FIB, which shows the IPv4 FIB. Like you can see the different prefixes, like for instance, that prefix is assigned on the interface loop 0. So it's a ARP adjacency. Damien is going to explain what an adjacency is tomorrow. That prefix, it's a /32, it's the local address. It's assigned on loop 0 as well, but that's not an ARP adjacency, it's a local adjacency. It's like, no, sorry, it's a neighbor adjacency. So you can see that that address is associated with that neighbor, that address neighbor. This one is local, because you can see here, this /32 is local, and it uses it's part of this prefix. You can do the same with IP6 FIB. Well, you have linked local addresses with IPv6, but it's the same idea. You see the prefixes that are assigned on the links, you see the neighbor addresses, you see the local addresses. And now, well, we just have to add some routes in Linux, because for now, Linux still does not know how to, I mean, Linux does not know that VPP is a router. So we just have to tell Linux to use VPP as a next stop for some routes. So to do that, this one actually exists. Okay. And now we should be able to ping from namespace 0 to namespace 2. So right now, if I show the picture, we have pings flowing from that namespace here, going to the bridge, going to the loopback interface, to VPP routing, to the tap interface, and here to Linux. And Linux is responding to those pings. And here we are, it's the end. Here you have a few commands to help you clean the namespaces that you created.